All right, here we go. By the end of this lesson, you'll be able to identify the forces acting on objects and draw free body diagrams correspondingly. A force. Ready? Lock in. Push or pull that causes acceleration if unbalanced. Force is a push or pull that causes acceleration if unbalanced. It is a vector, so it's magnitude and direction. The magnitude is how strong the force is. And the direction is which way it is pushing or pulling. Which way it is pushing or pulling. Yeah. With that, we're going to learn about the 6 different types of forces that we're going to use the rest of the semester. Okay. Should have made this a pre-quiz video, but homework right after a test, that's kind of okay.
I'm not done writing that.
Okay. So when we look at forces, the variable for a force is a capital F. We're going to have 6 different types of forces. So to make a distinction between the forces, we're going to do little subscripts. So the first one is gravity. We're not going to do this. It's going to be F little, like subscript G. Does that make sense? So that's how we distinguish what type of forces we're looking at. Okay. So here we go with the forces. The first one is force of gravity. Okay. This is force from the earth. Force that pulls everything towards, or let's go straight down
Towards the singular point of gravity.
Straight down towards center of the earth. Force that pulls everything straight down towards the center of the earth, like people in Australia or in the southern hemisphere are not like those. They're like hanging onto the grass, like they're not. They're towards the center of the earth.
Well, basically the point of the earth.
Okay,
It's
and it's created by the earth. There's force gravity. All right, big misconception here. People are thinking, oh, force of gravity is equal to negative 9.8 meters per second squared. What measurement corresponds to meters per second squared? Acceleration, not a force. Okay? Not equal. That is not the same thing. Okay? This is the acceleration due to the force of gravity acting on an object. Think of it in free fall. Okay. This next thing is going to hopefully help you break this wrong connection. Another name for force of gravity is weight. how much you weigh, that's how strong force of gravity is pulling down on you. Okay? In America, we measure your weight in pounds. Physics class, we would measure your weight in newtons, which is the unit of force. Good with that, so how heavy you are, that's the force of gravity. Okay. Good with that? Okay. Number 2, friction. So friction's kind of the exception to this pattern of capital F sub. We're gonna write some other subscripts under that, so just to keep things simple, we just write a lowercase f, friction. What causes friction is the roughness between surfaces. And the roughness between surfaces is what causes that. The direction, and always acts in the opposite direction to the way surface wants to slip or slide. Always acts in the opposite direction to the way the surface wants to slip or slide. And always acts parallel to the surface. Always acts in the opposite direction of the way the surface wants to slip or slide. And always acts parallel to the surface. Friction. Good. Always acts in the opposite direction to the way the surface wants to slip or slide. Always acts parallel to the surface. Good. Air resistance caused by millions of collisions with air molecules. You stick your hand outside of the window of the car, that's the feeling of collisions with millions of air molecules, okay? It always acts in the opposite direction of motion. Always acts in the opposite direction of motion. Good. Halfway done.
This is how planes work, quite literally.
Yeah. Okay.
Does this mean you have to start like accounting for air resistance when you do so?
Great question. I will hit that in about 10 minutes. It's a great question. Okay, next up, this one's kind of the weird one. Normal force. Can inanimate objects, non-living objects exert force? Quick story. Roommate in college, his job in the summer was a backpacking guide out in Colorado. The tents that he had did not shed water well. And so in the middle of the night, if it was raining, one of his responsibilities was to push up on the roof of the tent and let the water fall off, like while he's in the tent, okay? So he comes back to Purdue, and we're in the dorms. Our beds are lofted, meaning it's like a bunk bed without the lower bunk, so we're sleeping close to the ceiling. We go to bed one night, and it's raining. He wakes up in the middle of the night, sees the roof of what he thought was the tent, like right here. Because we're sleeping elevated, close to the ceiling. So he goes to push on what he thinks is the roof of the tent, and it doesn't go anywhere. He's like, oh my goodness, that's a lot of water in there. He starts pushing harder and harder. He starts two hands, and like pushing as hard as he can. I wake up to him. He's got both hands, both feet planted on the ceiling, pushing as hard as he can. Like, no! I'm like, Mark, wake up! What is going on? I was like, oh my goodness, I thought I was gonna die. Like all that water was gonna crush me. Makes sense what was like his bed is like bowed crazy. So as he was pushing on the ceiling was pushing back on him. You okay with that? Like junior high physical science here, Newton's third law. Okay, for every action there's an equal and opposite reaction. He's pushing on the ceiling pushes back on him. Okay? The ceiling was exerting a force on him. He thought he was going to get crushed. Okay? We're going to call that normal force. This is a supportive force from a surface. It's a supportive force from a surface. Now, normal, it is a geometric adjective, kind of a weird adjective. It's like, we got a weird force coming up. Like, okay, normal means perpendicular. I think it's a Greek origins that meant sober. If you were normal, then you were standing upright to the ground. If you weren't normal, you had a hard time standing upright perpendicular to the ground. So normal force always acts perpendicular to the surface. Always acts perpendicular to the surface. Normal force. Okay? Next up. Tension. Okay, this is a pulling force from a rope or string, cable, you know, that type of stuff. Rope or string, a pulling force from a string, tension, always acts parallel to the rope. Actually, let's do this. Always pulls parallel to the rope. Always pulls parallel to the rope. Last one. You guys have like a miscellaneous drawer in your house. Like, I don't know what to stick with. Miscellaneous drawer. This next one's the miscellaneous drawer. Okay. Applied force.
It's just a lot.
Okay, applied force. This is a force from a living object or machine.
Or in case additional force.
Applied force. Okay, a force from a living object or machine. Good there? A lot. Would have made a good pre-quiz video, yeah. Okay, let's learn how to use them. Okay. It's called a free body diagram. I would not worry about writing this, just, this will come to you. This is just, so we only draw forces acting on an object, center of mass, only draw forces, not velocity, acceleration, displacement. We only draw forces acting on the object. We'll hit all these. So they're on the video, they're in the PowerPoint. Here we go. Okay. You standing on the surface. Just standing on the ground at rest. Okay. What forces are acting on you? So we're going to represent you as a box with a belly button. That belly button is the center of mass. So it's going to act as our origin. Okay. So acting on you, force of gravity, that's kind of a give me. If we're on the surface, on or near the surface of the earth, just force of gravity, like this. Okay. And are you in free fall right now? No. What is preventing you from being in free fall? The ground, which is exerting what type of force? Normal force. Perpendicular to the surface. That would be the free body diagram.
And force is measured in newtons.
Correct. Yep. Okay. So that's a free body diagram.
That's what we want to measure.
Good.
How much.
Okay. Next. Doing okay there? Yeah. Kicking a box. While my foot is in contact with the box. What is the free body diagram? Give it a best shot. Free body diagram is the box being kicked. Oh. Quick little side note. Always include friction. Always ignore air resistance. Unless the problem tells you to do something different. Okay, always, the default is include friction, ignore air resistance. Unless the problem says to do something otherwise. Good with that?
Are these like vectors, like you have to make them like longer and shorter?
Great question. The question was, vectors, do we need to make them longer or shorter? If we were to doing it to scale, yes. This just kind of gives us a platform. You can if you'd like, but I'm not gonna grade that. Okay. Thumbs up when you have a guess. Okay, gravity, normal force, being kicked by the foot, so applied force, and there's friction, it opposes the way it is slipping or sliding. How did we do? Okay? Free body diagram. Okay? The next question is a follow-up question, is the box has been now kicked and is now sliding along the surface. Okay? What does the free body diagram look like? Oh dear. While it's sliding along the ground. So I've done, kicked it, and sliding. What does that free body diagram look like? Thumbs up when you got a guess. Ready for this one? I think a lot of you are going to learn something. That's the free body diagram. Okay. What? Okay, so once it leaves my foot, I no longer exert a force on it. That would be really cool if I could, like, but once I leave contact, I no longer exert a force on it. So what keeps it moving? Why is it moving that way? Okay, yes, velocity. There's something more foundational. Inertia. Okay? Here's the story of inertia. Initially, the box was at rest, and its inertia is like, dude, I just want to stay here. And then the force comes up from the foot and kicks it. It's like, oh, I do not want to do this. Okay? But once it's moving, then it's like, okay, I'm moving, let's just continue to do this. And it wants to keep moving. That's inertia, not a force. Inertia is not a force. It's just the object's natural tendency to do whatever it's doing. And friction's like, let's slow you down. Like, ah. How are we doing with that? Okay with that? Personifying inertia, like it's a good conversation to have. Okay? So that's your free body diagram. Nothing acting in the direction of motion, that's just inertia. Okay? Bucket being raised at a constant speed. Bucket being raised by a rope at a constant speed. Thumbs up when you have something. Force gravity going down, tension going up. There is no normal force because there's no supportive surface. Okay, it's not resting on the ground or a surface. Good with that? Yeah. stapler on an incline at rest. Here's my recommendation. Anytime you find yourself the object on a hill, an incline, or ramp, is draw the surface tilted at the incline and draw the box kind of on that tilted incline. Okay, I'll walk you through this one. This is a little more involved. Is gravity going A or B? Gravity goes straight down towards the center of the earth, A. Okay. Normal force. Is normal force going A or B? Normal force goes perpendicular to the surface. That's what normal means, is perpendicular. Correct answer is A. Okay. What is preventing the stapler from sliding down the ramp? Friction. Are we okay with that? To figure out the direction of friction, here's the trick I'm going to coach you to say. It's like, look at the ramp. Look, like pretend this was icy.
I can see that.
Like no friction. Which way would the object which way would the object slip? Down the ramp. Friction opposes that slipping or sliding. Friction goes up the ramp, parallel to the surface. That's your free body diagram for the stapler. Good with that? Questions there? This one, a little bit involved. Pretend you're doing a wall sit. You know what I'm talking about? Gym class. Hold that for 5 minutes.
Or doing exercise,
Okay.
some sort of like the chair squats.
What forces are acting on you? See if you can figure that one out. Yeah. You're good. Gravity. Normal force from the tree, from the ground. Okay with that? If the tree didn't exist, what would happen to you? You'd fall backwards. So it's supporting you. Which way is the tree exerting force supporting you?
Right.
Perpendicular to the surface. So, one side note, it is legal to have more than one type, the same type of force. Just from different surfaces, okay? If this was icy, which way would your feet slip? So friction is going to be acting which way? Okay? If the tree was icy, which way would you slip? Down. So friction from the tree
Straight up under an ice storm.
is going up. So, this is from the ground, that's from the tree. You can have more than one force going in the same direction. That is also legal.
Tree.
Okay? Good with that? Press. Beautiful question. So what I care about, what I care about is the forces acting on the person, on the object, not the forces that the person is doing or the object is doing to the work. Okay? Okay? You pulling on a rock with a rope. So I have you for 3 minutes. Hang on. 3 minutes. You got 2 more, one and one more after this. Free body diagram of the rock. Okay. That's the free body diagram of the rock being pulled by a rope. Okay, I'm gonna call that tension and not applied force because what's touching the rope? Sorry, what's touching the rock? The rope, not the person, okay? Notice this is at an angle, a little foreshadowing. Okay, last question. Same scenario, free body diagram of you. We have gravity, we have normal force. If this was ice, which way would your feet slip? Slip that way, so friction's going this way. Does that make sense? Enabling you to move. Okay? Tension, is that acting A or B? What I care about is the force acting on the person, not what the person is doing. Which way is the rope pulling on the person? B. So this would be tension. Okay with that? Just a little side note, these would be considered Newton's third law.
Yes.
For every action, there's an equal and opposite reaction. Good with that? Woo! Okay, your homework tonight is a free body diagram worksheet. Just doing the free body diagrams. There's day 1 and day 2. Just do day 1's, just doing free body diagrams.